Hello and thank you for watching. In this video, you will learn how to write equations explicitly in terms of x, evaluate a function at a given value, and also use a graph to find the value of a function. We'll begin by first going over what an explicit equation means. An explicit equation is simply an equation solved for a specific variable. For example, y is equal to 3x squared plus 6x minus 9. This is an example of an explicit equation. It explicitly is in terms of x, and we have explicitly solved for y. We know that y is equal to, again, this expression right there. An implicit equation is an equation that is not solved for a variable. So for example, 3x squared plus 4y squared is equal to 9. This is an implicit equation. This equation is not solved for x nor for y, so it's not explicitly telling me what the value of any of these two variables equals to. So what we're going to be working on right now is how to write an implicit equation to an explicit equation in terms of x, meaning we're going to write it with x as y variable. So we'll be solving it in these situations for the variable y. So we begin with our first example. From Algebra 1, we have a linear equation written in our standard form, and we want to write this equation explicitly in terms of x, which means that we want to solve this equation for y. I explicitly want to know what y is equal to in terms of x as the variable. So I begin by doing my algebra thing and moving the x to the other side. So I end up with negative 4y is equal to 20 minus that x. I then divide by negative 4. And I get that y will equal to a positive 1 over 4x minus 5. I just kind of switch these backwards. This gives me negative 5. Since this is negative 1 over 4 is 1 over 4. So I wrote that just as 1 over 4x minus 5. So this equation is explicitly in terms of x. You see right here, I know exactly that y is going to equal to this equation explicitly in terms of x, where x is the variable. Let's look at another example. Here we have the equation of a circle. So to write this explicitly in terms of x, again, just like before, I'm going to move the x to the other side and y to the second power will equal to 25 minus x squared. In this situation, since I have y to the second power, the inverse operation to that would be to take the square root. So y will equal to both the positive and negative square root of 25 minus x squared. So there, I have written the equation explicitly in terms of x. For my third example, I have not a circle, but I still have a situation where my y term is being squared. Notice that all of this is being squared. So I'll start again first by moving the x to the other side, and y plus 1 squared is equal to 3 plus x. Now here I want to move the 1 to the other side. I want to subtract that 1 to both sides, but I can't do that because again it's being grouped to the y because of the square. So to get rid of that, I'm going to take the square root. So again, by taking the square root, we can cancel out that square, and we now have y plus 1 is equal to still the positive and negative square root of, I'm going to switch those terms, x plus 3. So now I can move or subtract the 1 from both sides, and y will equal to x plus 3 minus 1. And make sure that I indicate that the minus 1 is not underneath the square root. So let me just do that, just so we can again put a little tail to it, and whoever's reading this hopefully understands that, okay, I'm subtracting 1 from the square root of x plus 3, from the positive and negative square root of x plus 3. So this equation is now explicitly in terms of x. Again, we know y explicitly equals to all of this where x is the input, my variable. Now let's work with radicals. In order to solve this equation right here, again, in terms of x, we're going to move our x term to the other side. So we're going to subtract that 2x squared from both sides, and we have negative 1 times the cube root of y is equal to 7 plus 2x squared. We're going to divide everything by a negative 1. I'm sorry, that should be minus. And we're going to divide everything by negative 1. So the cube root of y will equal to a positive 2x squared and a minus 7. Now here, since we have the root, the opposite of getting a root is raising it to a power. So we're going to raise this to the third power, so the root and the 3 can cancel each other out. They'll inverse operation, so then we end up with y is equal to 2x to the second power minus 7 raised to the third power. And this is our equation explicitly written in terms of x. So we know explicitly that y is equal to 2x squared minus 7 all raised to the third power. Another example with the roots, this time we have a square roots. Remember here our index is invisible, so that means that our index is a 2 there. So we'll start by moving the x to the other side. We have a negative sign in front of it, so that's a negative 1 times the square root of y plus 1 is equal to 8 minus, again, the x. We're going to subtract the x from both sides. Similar to the last example, we're going to divide by negative 1. So we end up with y plus 1 is equal to, I'm going to rearrange the two terms, a positive x and a negative 1, so x minus 8. And this time, we're going to raise it to the second power since our index is 2. And we end up with this. Well, just like the last example, we want to move or subtract the 1 from both sides, so we could again explicitly solve this equation in terms of x. So we know that y will then equal to our y minus 8 to the second power and then minus the 1. So this is our equation explicitly written in terms of y. I'm sorry, in terms of x. It's solved for y, which means that it's in terms of x, since those are the two variables that we have. Now, this last example here on writing equations explicitly in terms of x is a trickier one, because you'll notice again that while we want to move this x or this term that has an x, we can't, because again it has also a y term. So to write an equation explicitly in terms of x, again we're solving the equation for y. So here the trick for an example like this, where we have two terms that have y and we can combine these two terms, is to move everything else. So we'll keep the x term, the xy, and the minus 5y on the left side of our equation. We'll move the 1 to the other side, so we add 1 to both sides, and we now have that 5x minus, sorry, xy minus 5y is equal to 2x plus 1. Now here's the trick. Not much of a trick, just some algebra. Since both of these terms have the y, and then we can combine them, then we're going to use some algebra here and factor out the y. So we're going to keep the x minus 5 in the parentheses and factoring out the y, multiplying it out or dividing it out essentially, so using it, making it look like distribution. So where if I multiply it back in, I end up with this right there. That's going to equal to 2x plus 1. So all I've done is simply used the reverse of distribution and factored out the y, so I have again the product of these two things. And now I can divide. Dividing both sides by x minus 5 will reduce these two terms. They're common factors, so reduces simply to 1, and we end up that 1y is equal to 2x plus 1 over x minus 5. So this is going to be our equation written explicitly in terms of x. Now, The next thing we're going to discuss in this video is the function notation. Function notation is just as a variation of an equation where we use function notations to represent that equation. So for example, we'll do a very simple linear equation, y is equal to 3x plus 4. And function notation is simply recognizing that the value of y, which is the same thing as the symbol f of x, that's how we read this. We read this as f of x, can replace the variable y, and we can write our equation as the function 3x plus 4. So in very layman's terms, it just simply means that we're replacing y with this notation of f of x. Now f is just the name of the function, x is the input variable. So replacing any of these, replacing f with another letter like h, g, w is just simply changing the name of the function. Changing this right here changes this input. So while f of x is equal to 3x plus 4, I can rename this and call this h of y, which would be simply 3y plus 4. Same function, same equation, is just using a different name, h, and a different input variable, y. Okay? So there's there's a variety of different ways we can represent the same equation with a function notation. It's the same thing. So if I plug in the number 3 here and get the answer of 13, it'll be the same thing here. When I plug the number 3, I'll get the same answer of 13. So let's look at how we evaluate these functions. Well, evaluating a function again simply means, as you see right here, we want to know what f of negative 5 is. So what we simply do is replace all of these x values, as you see right here, with the number negative 5. Because that's what the function, what I want to evaluate this. I want to figure out what f of negative 5 is. So this is negative 5 to the second power minus 6 times negative 5 plus 23. Which simplifies to 25 plus 30 plus 23, and plus 30 because again negative and a negative. I'm subtracting a negative 30, which is the equivalency of adding 30. And then adding these three things here, that's going to be a total of 78. So f of negative 5 is equal to 78. And now remember, f of x is the same thing as y. So what we've basically done is that we plugged in the number negative 5 in for x, and we found that the y value is 78. So we have again this ordered pair that we can then use to simply plot it on a coordinate, on an x and y coordinate plane. This is not drawn to scale obviously, and we know again that we have a point on the graph. We have that point there. That's what this again means. This right here means the exact same as that, which then could be represented as a dot again on our coordinate plane. Let's look at another example. So here, just simply substituting in 4 for our x value, we end up with negative 3 to the 4th power. Well, negative 3 to the 4th power is equal to 81, because negative 3 to the 4th means we have negative 3 times negative 3 times negative 3 times negative 3, which is 9 and 9. So 9 times 9 is 81. Now, and again, we have to do that first just by simply following order operations. Now we can now multiply 5 with 81, which is a total of 405. So h of 4 is equal to 405. Now, we can also plug in other stuff other than just numbers. We can apply this function notation and use it to evaluate a function at, let me change this to a g, that should be a g, at different other expressions. So like example, on this one right here, we are replacing the x value with the expression of 3y to the second power. So this x value here and this x value there, which are being raised to the 3rd power and to the 2nd power, as you see right there, I'm going to replace with the expression of 3y squared and 3y squared. Now, by our exponential rules and properties, this means that 3 is going to be raised to the third power in the first parentheses. Let me just color coordinate this. In this first parentheses here, 3 is going to be raised to the third power. And y to the second is going to be raised to the third power. In the second parentheses here, 3 is going to be raised to the second power, and y to the second is going to be raised to the second power. And I'm adding those two values together. So let's see what we end up with. Well, 3 to the third power, that's equal to 27. Here, to simplify this, we multiply our exponents. So that's y to the sixth power. 3 to the second power is 9. And just like the last one, to raise the second to the second, we multiply those exponents. So that's going to be 4. Y to the fourth power. And this is the answer that we're looking for. This is how we evaluate this. So we end up with 27 y to the 6th plus 9 y to the 4th. And again, well, obviously, we shouldn't have to explain this, but I'm just going to make sure we go over it, because this is y to the 6th and y to the 4th. These are not the same degrees, thus they are not like terms. So I cannot combine these to get a total of 36. 36. So I end up again with these two separate terms. And this is again the simplified form of this. Now, this last example, again, just to show you another example how we can evaluate a function using, again, another expression. Here we are substituting in 2a plus 7 into these x values. So we want to evaluate k when x is replaced with 2a plus 7. So 2a plus 7 to the second power minus 2a plus 7 minus 1. For this part right here, I'm going to simply use again the rule of a perfect square binomial, which is just this. I know that any perfect square binomial can be expanded out and written as this trinomial here. And we'll start off with this a squared. This a squared is this part right here. So I want to raise 2a to the second power, which is going to be 4a to the second power. The middle term, which is plus 2ab, so let me put my plus sign, 2ab is going to multiply a and b together, which in this case are these two values there, and then double it. So 2a times 7, that's 14a, doubled is 28, so 28a. And then the last term of the trinomial would be b to the second power, which in this case is the 7. So 7 to the second power is 49. So these three terms is just simply the product. These three terms right here is simply this to the second power. I haven't done anything else. So for example, this is just simply the distribution of this negative sign to everything inside there. So that's going to equal to negative 2a plus 7. And then finally just simply bringing the minus 1 down. I can then combine like terms. And I can combine the 4a squared, well, with nothing. I can combine the 28a with the negative 2a, which is positive 26a. And then I can combine these three constants, which adds up to a total of 41. So k of 2a plus 7 is equal to this trinomial there. Now, if you're not familiar again with this definition of a perfect square trinomial, then you can just simply use distribution. Recall that, let me put it in red. Recall that 2a plus 7 to the second power simply means 2a plus 7 times 2a plus 7. And multiplying this out using either distribution or using this box method here, 2a plus 7, 2a plus 7, we end up with 4a squared, positive 14a another positive 14a, because 7 times, multiplying again all of these things now by 7. 7 times 2a is 14a, and then 7 times 7 is 49. We will end up again with this exact same thing. As you can see, we have the 4a right here. The 28 is when we combine these two. Those add up to 28a. And the 49 is right there. So you see, you could do that as well, if you, again, don't want to do this. Now, going back to evaluating functions at numerical values like numbers 7 and 8, we can also figure out the value of function using graphs. Because remember, when we evaluate a function, f of x, that's simply equal to the value of y. We're basically just looking for the y values here. So if I want to know what f of 1 is equal to, I'm going to look at where x is equal to 1, and I see that the graph, which is again this parabola here, this graph has a y value at negative 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, negative 9. So my answer is negative 9. F of negative 2 means that when x is equal to negative 2, which is right here, the y value is equal to 0. That red dot here is at negative 2, 0. This point down there was at 1, negative 9. So when x is equal to 5, 5, 1, 2, 3, 4. We have a y value at 6. So there's your answer there. And when x is equal to 0, the y value is negative 8. So this is how you use a graph in order to evaluate and find the function value at those 4 respective places, at positive 1, negative 2, positive 5, and at 0. Simply looking for the y value on the graph at those x coordinates. Okay. Well, again, thank you for watching. If you do have any questions, again, don't hesitate to email. Thank you again for watching, and hope you have a great day.